Let's now talk about the idea of the chain rule as it applies to tangents of parametric equations. So let's consider the function x equals 24 times root 2t and y equals negative 16t squared plus 24 root 2t. And that actually represents a projectile launched at 45-degree angle. Now the parametric equation will tell us where it is, the location of this projectile as it's been launched at any time t, but will it tell us about theta, the angle? In other words, the tangent to the curve or the path that it's following. Let's start off with a theorem. If a smooth curve C is given by x equals f of t and y equals g of t, then the slope of the curve C at xy is given as dy dx equals dy dt over dx dt. And the proof of this, or the justification for this, comes directly from the chain rule. Now, we have some parametric curve. Oh, actually, this is talking about a point. This point has coordinates x and y, which can also be represented as f of t, g of t. Now, this point is some point on a parametric curve. I have two representations of that same point. I can think of it in terms of Cartesian coordinates, x and y, or in terms of the parametric function where the coordinates are given as f of t and g of t. So what I want to do is I want to find the derivative. So if I take the derivative, dy dt, recall that y is actually a function of t, but y is a function of x. So what we're actually going to be doing is just applying the chain rule. Dy dt is going to be equal to dy dx times dx dt. That would then imply that dy dx is equal to dy dt over dx dt. Okay, let's take a look at x equals root t and y equals t squared plus 3t. And what I want to do is I want to find the derivative dy dx. Okay, I know that dy dx will be dy dt over dx dt. Well, let's see, dy dt equals derivative of y with respect to t is going to be 2t plus 3. dx dt is going to be 1/2, t to the negative 1/2. Therefore, dy dx is 2t plus 3 over 1/2 t to the negative 1/2. So at any time t for this curve, we can actually figure out where or what the angle is, the tangent to the curve, as, of course, a function of t. Now, a curve C represented by x equals f of t, y equals g of t on some interval is called smooth if f prime, that's the first derivative, and g prime, the first derivative, are continuous on this interval I. Make sure you understand that's an I, not an L. Let me fix this one so there's no doubt. And not simultaneously 0, except possibly at the endpoints. The curve is called piecewise smooth if it is smooth on each of some subinterval. So something that looks like this, a parametric curve that perhaps goes like this, this is smooth. Something that would be piecewise smooth is supposed to have a function like a cycloid. Here it's smooth on this interval, but not at this point, and it is smooth on this interval, but not at this point. So this is smooth, and this is piecewise smooth. Okay, consider the Prolite Cycloid given by this function x equals 2t minus pi times sine t, and y equals 2 minus pi times cosine t. Now, if I were to graph this, what this looks like is something like this. Yeah, I kind of made this too big. Yeah, that's good enough. That's okay. Now, let me go ahead and redo that. Yeah, let me make it a little bit more realistic. This could come more like this. This could be a smaller loop. There we go. Well, like I've said many times, an artist I ain't. But that's what the prolate curve, that's what this particular prolate curve is going to look like. So what I want to do is I want to find the derivative as a function of t. So dy dx is equal to dy dt over dx dt. So dy dt, here's y. This is going to equal pi sine t divided by the derivative here is going to be 2 minus pi cosine of t. So first of all, let's go ahead and find the slope. The rate of change of this curve at t equals 2 pi. Well, that's going to be equal to sine, or pi times sine of 2 pi divided by 2 minus pi times cosine of 2 pi. Well, this is 0. And let's see, as long as this is non-zero, I'm in good shape here. This is a negative 1, so this could be 2 plus pi. So this slope is 0. Well, that's right here. This is going to be 2 pi. So my slope at 2 pi is going to be 0. It's horizontal. And now let's take a look at it and let's find the slope at t equals pi over 2. Well, that's going to be pi times sine of pi over 2 over 2 minus pi times cosine of pi over 2. Well, sine of pi over 2 is 1, so this is pi, over cosine of pi over 2 is 0, so it's pi over 2. So when t is pi over 2, which is going to be like somewhere in here, roughly, the slope of the tangent line is going to be pi over 2. Okay, note if dy dt equals 0 and dx dt is non-zero for t equals t naught, some value of t on that interval, then the curve given by x equals f of t, g equals y, y equals g of t, that parametric curve, has a horizontal tangent line at f of t naught, g of t naught, which makes sense because remember what we have is dy dx equals dy dt over dx dt. So if the numerator is 0, which is what they're saying right here, and the denominator is non-zero, well then that ratio is 0, and that's a horizontal slope. On the other hand, if dy dt is non-zero and dx dt is 0, then the curve is going to have a vertical tangent line. Well, that makes sense too because remember dy dx equals dy dt over dx dt. What we're saying is that dy dt is non-zero, that's some real number, but dx dt is 0. Well, that gives me some constant, non-zero constant, over 0, which is undefined. And if I have a curve if the slope is vertical, then the slope is undefined. So that actually should make sense.